noise will mean that error will start creeping, so that will eventually limit it, like an error catastrophe, kind of, or error threshold kind of idea.
I'll talk about that a little bit later today. Noise will tend to weaken this signal. Now, these are random matrices, these are average statements. But anything that makes the mapping less exact, anything that perturbs the D matrix will tend to eliminate the effect. So there is, all of these have to be, I guess what you're saying is all of these have to be compared to a null model. But this is already a kind of null model with respect to selection, because there's no selection. But I'm not sure, since these are statistical averages, I'm not sure noise would really do
because
much.
the larger the vector of transcription factor regulating development, the more likely that you will commit more errors, so that will limit the number of phenotypes that would be realized.
Right. Maybe. That might be true, but again, the more the higher the dimension, the higher the density of your developmental matrix, and the stronger the effect. I think there's no way of getting away from that. So this, by the way, predicts things like this. It predicts that organisms that have a higher regulatory dimension, like us, should produce offspring more like us than bacteria. Because one of the mysteries of heredity is why we produce offspring that look so much like us. Why doesn't my offspring look like another species? We have most of the genes with others, we share most of our genes with other species. And the argument here is that actually it's because of this kind of bureaucracy of the developmental matrix that the constraint is so severe that you can't escape from that local space. Now, in some audiences, they'll say, you know, a single projection is too simple, those more interested in mathematics. You have to look at the current projections. You have to look at the dynamical system, not just linear algorithms of motion. And I'm not sure how technical this audience is. And it goes through some things very fast for the one or two of you who are. Okay, so apologies to those who are not. It's been known for a long time that when you write down models like the one I just told you about, there are a certain class of logical functions that it cannot compute. So if you have a single projection mapping, it can solve logical problems in the class, in a simple class of Boolean functions like the OR and the AND function. Can't compute the exclusive OR. How many of you actually have any knowledge of these kinds of things? None? Oops. Okay, it only gets worse. So this is something you absolutely should know, by the way, irrespective of what I'm telling you. And that is that it's quite interesting. Does everyone know about OR and AND functions? So, surely. So basically, you know, there are truth tables that all worked out, right? Here, let's go. And when you, so you write down, your inputs would be like 1, 1, 1, 0, 0, 1, 0, 0, and you write down a truth table. Right? So the OR function would give you a 1, 1, 1, and a 0. Because you can have a 1 or a 1 gives you a 1 or a 0 gives you a 1, 0, 1 gives you a 1. Right? The AND function would give you only a 1 here and 0 everywhere else. Okay, because you have to have both bits on. Right? And the exclusive OR has this property. And so this is the basis of all digital computation. And so now, if you think about it on the plane, 0, 0, 0, 1, 1, 0, 1, 1. With a single line, I can define both the AND and the OR function. Here. But how can I draw a single line and generate the exclusive OR? You can't. There's no single line, or in higher dimensions, hyperplane, that can separate the points. And so for this, you need two. This is called polyhedral separability. And so if development has transcription factors as input, so this is a vector with two elements, 1, 0, 0, 1, so on. Higher dimension, and it needs to create different states of the organism, right, in response to those inputs. Okay? And they have this feature that they don't conform to very simple basis functions. Then development has to do polyhedral separability. And polyhedral separability, for those who are interested in such things, is NP-hard. So you can show the so-called K separability of these K hyperplanes. Does everyone know what? Do you know what NP-hard? Do you guys know about computational complexity? So NP-hard means that it's basically a random search to find a solution, but validating the solution takes polynomial time. It's very quick. So once I have a solution, you know it's right or wrong. You tell me, oh, that's right. But finding the solution takes forever. So if development has to do polyhedral separability with these recurrent networks, it's actually a random search. So another tool would be to show you that development uses so-called approximate algorithms, which don't have the NP-hard problem. I mean, that's another tool. Final remark for the even more sophisticated of you in this domain is the so-called Sabenko theorem. And this is that sums of sigmoids, this is the definition, are so-called dense in the unit square. This means that this is a universal function approximator. This means that a two-layer developmental plan, or perceptron, is a universal computer. It can calculate any function. So any categorization of the kind that I showed you up there can be performed by a developmental plan with two projections, any. And this is proven. So it's kind of interesting, by the way, that in development you do tend to have at least two, right? You have transcription and translation. So an interesting sort of philosophical aside is whether or not that was critical. Because with a single one, there are quite elementary categorizations of the inputs that you could not separate. Okay, and the final one for the statistical physicists, I'm trying to appeal to every one person, is the so-called random matrix theory, which you might be familiar with if you do statistical physics. There are some very interesting and hard problems in random matrix theory that haven't been solved that we need to solve some of the problems that we're dealing with now. Because most of random matrix theory comes from sums of random matrices, and we're dealing with products of random matrices. And because matrices multiplication does not commute, it's very hard to do analysis. And so there are some really hard technical problems in doing mathematical developmental biology because we don't have the tools from statistical physics that we need. So there needs to be development in random matrix theory. For the one person or half a person in the room who's interested, we can talk about it afterwards. The consequence, though, of all of that stuff is it makes it worse. And so the proportion of visible phenotypes when you have recurrent plans actually goes down way below the single projection. And it's worse for the random non-stationary Markov process than the stationary. It doesn't really matter. Again, the message that I told you remains true, it just gets worse. Too much. Alright, final point. Let's imagine an evolutionary sequence. You have a bunch of genes, and by duplication, you take some vector in the developmental matrix and you duplicate it. So a standard assumption, by the way, in evolution is that evolution proceeds by duplication and deletion. So you take a gene, you copy it, it's neutral, maybe it does something new, you keep it, or if it does nothing, it just goes away. It's a pseudogene. So you could take our model and you could actually subject it to an evolutionary dynamic, right, where you duplicate genes, make the dimensions of the D matrix bigger. And if you do that, you have the following observation. And I'll just stick with the observation. Imagine make a phylogenetic tree of all phenotypes in the world that come out of this dynamic. And there's an ancestral developmental matrix, and it produces descendants, and they produce descendants. So the black square on this tree, which is a phenotree, it's a tree of phenotypes, not of genotypes, you'll notice are dotted all over the tree. Whereas the descendant species are localized to branches. So the ancestor spans almost the entire morphological space, whereas the descendants are more concentrated. So I told you earlier that this follows from the increase in the regulatory dimension. Low dimensions, you get a huge amount of what gets called by evolution as disparity. That's the embedding of diversity in the metric space, distance between things. But later in time, you don't get as much disparity. You get more diversity because you produce more species, but the species are all the same. So this is the first and second principal components through the phenotypic vector space, where the axes of the ellipses are the mean and the variance. People here know about factor analysis. Okay. So the point being here again that in the volume, in the principal dimensions of phenotypic space, the volume of the ancestor is larger than the volume of the descendant. And I mentioned this again back to Gould. If you read his book called Wonderful Life, one of the points that's been made extensively about the Cambrian radiation is that you get a lot of phyletic diversity. So a lot of species came into existence there, forms came into existence. And later in life what happened is we just filled in locally the variability, but it spanned a huge amount of the morphospace. Okay? And this is completely consistent with the idea that early in life you were living in a time of lower regulated dimension. And that as you tuned regulation to make yourself more responsive to different environments, you also imposed more constraints. And so early you have phyletic diversity high, but species diversity low, disparity high. Late you have species diversity very high, but phyletic diversity relatively low. Now, I'm nearly finished. Jess and I went to visit a friend of ours, Doug, who I mentioned at the beginning, Doug Owen, who is the curator of the Burgess shell at the Smithsonian Museum of Natural History in Washington. And we were very lucky because we could go and look at these things, and it's not easy to see. And you expect, when you go and see the Cambrian fauna, right, to see beautiful, amazing fossils, and of course this is what you see. And it's like, Doug, where is it? Where is that fossil? Well, you see, this is really that. And if you just sort of rotate it a little bit in your imagination, so biologists, like archaeologists, can turn a single rock into a pyramid, right? It's like, but anyway, it's a bit disappointing for us. We expected something more grand. Let me just make one final point about this being a general principle. This looks a lot like a statement about development. For those who don't care about biology, those kinds of models I showed you could be quite general models of regulation. After all, neural networks were invented to study brains, not to say development. And I'm going to show you this because I think it does actually apply to corporations. And this event relates to a discussion we were having at dinner. So, who are these people? Come on. Who's that? Who's that? Huh? Oh, fail. Okay. Paul Allen. Paul Allen. Who's that? Yeah, and okay, good. Thank you. 3 out of 4, not bad. Now, around the same time, you build companies, and what's the difference between these companies? Well, one difference back then was the size of it was effectively the regulated dimension of Microsoft versus Apple. Microsoft is a very large firm with many bureaucrats. Now, by our theory, what does that mean? It means you can produce many types, but they're all the same. That's what it says. Right? When you're smaller, like this company used to be, you can produce fewer types, but the types you produce are very different. And we all know that's true. If you work in a large company, of course you can make more product, because everyone has to produce, but everyone is producing exactly the same product. And it's because of the interactions. You're not allowed to innovate. So I think that the principle is very, yeah, Jeff, I get you, is very generic. And we see it wherever we look. And it's one of the reasons, by the way, why the Scientific Institute consciously decided to remain small. Because we have to keep a small bureaucracy so as not to converge in this smaller volume of solutions. And so it is a general ergonomic principle. Jess, yeah.
So you're making a point about the distinction between diversity and disparity?
Yeah, but diversity and disparity, because thanks. So again, diversity just counts the number of points. So the number of points will always increase as you increase the dimension. But they're all getting more closer in an embedding. So yeah, one is a measure of just the number, the cardinality of that set, and another is actually a statement about metrics, distances. Complexity, by the way, which will be later. So diversity, number, disparity, typically a continuous measure of similarity. So now it could be KL divergence, entropies, and so on. Complexity is usually a measure either of the time it takes to make diversity, right? The compressibility of your diversity, factorizability of it, or the description of the program required to generate your diversity. So there are three classes of complexity measure: time, informational, right, in terms of compression, and algorithmic. Okay. And so I haven't talked about it, I'll talk about it a bit later. I think that's that. Summary, again, quickly. The construction dynamics, a very general approach to diversity. Okay. Shows you how you can get more of it ecologically, but it also sort of integrates a little bit across development and ecology. But I showed you that there was a fundamental dilemma, that it's not, I didn't go into game theory, but you can show that it's not an ESS, it's not a Nash equilibrium in the game. It can be algorithmic or Darwinian on a continuum according to the strength of competition and noise. So development looks different from ecology because it's fundamentally different for these reasons, in part. That once you have construction, it has imposed significant constraints on variability, along the lines I just told you. And that the more complex the construction, the more evident its footprint. So at a certain point, right, when a bureaucracy becomes so big, all of the structure is the bureaucracy rather than the constituent contributions. So that's Microsoft. Now it would be inappropriate of me to talk about complex systems without talking about von Neumann, because he's one of the key figures in the history of the field. And in the 1940s, von Neumann is very important, certainly in mathematics, mathematical physics, quantum mechanics, co-inventor of the digital computer, worked on the Manhattan Project. Von Neumann was became interested in biology, and in particular in replication. And very quickly he realized that replication is a trivial problem. It's very easy to make something replicate. And again, we'll talk about this later. So he became interested in what he called his universal theory of construction. In 1948, he gave a lecture at the Institute for Advanced Study on the theory of universal construction, where he suggested that all living systems have to have three components. And just to show you what was on this, and he wrote down an algebra of life. Okay? And the algebra of life said there are three components. There's a message, there's a structure, and what you need to do in living systems is that messages need to be replicated, two of those, and you need an automaton that does it, and that messages need to build structures. Okay. But you need to decide which of those automatons to activate, and that requires a third automaton that moves between replication and construction, proliferation and differentiation. It's a proto-niche construction model. He didn't articulate it in those terms. And so if you think, all living systems are then constituted of a structure plus a message. And the key for von Neumann was to cheat, or not to cheat, he said equal to the vector A, B, C. And this is a self-replicating constructor, because the vector it includes in it are all the components necessary to replicate and construct. He wrote down a formal mathematical model for this. And later in life, as Freeman Dyson got very excited about, when he wrote about this kind of stuff, he realized that in some sense, yes, so this thing we'd call something like a polymerase. This would be the ribosome, right? This is a ribosome. This is a polymerase. And this is a transcription factor. So in some sense, a little bit like Schrödinger in his life, von Neumann had algebraically intuited the tripartite constituents of all living systems. Stan Ulam, who was also working at Los Alamos at the time, showed von Neumann how you could turn this into a cellular automata model, which I imagine Eric has talked to you about. And he wrote down the specification of the first self-replicating universal constructor cellular automaton. So I think it's very that this theory of construction has been there all the time since the 40s in the background as the critical theory that we need to develop to solve problems of living systems. And it's interesting how it's been sort of neglected. This died, it sort of didn't really go anywhere. And it's not clear to me why, actually. Von Neumann moved on, worked in quantum mechanics and so on. But it would be inappropriate not to mention it, and so this is just a schematic that he drew before he was constructed. So here's some references. You can download all of these from a web page if you want to. And later I'll talk about complexity. Thanks.
Thank you.